as well as beautiful birds. In the ancient days, people used to detect forest fires from watchtowers. Even now, they are used in some areas. And now we are on the Ferncliff Forest Fire Observation Tower. It is in New York. Due to human error during observation and inability to cover larger areas, this method is not so effective in detecting forest fires. Forest fire detection based on watchtower observation and patrols proved to be unsuccessful because of human errors. In order to overcome those demerits, an advanced system was developed. That system was called satellite-based forest fire detection system. Particular limit, the captured area becomes pixelated due to low resolution. Because of this, small areas of forest fires cannot be detected. Another drawback is that when forest fires are blocked by clouds, it makes it impossible to capture the required data. The final demerit is the processing time. It takes about 2 days to capture the entire surface of the earth before the interpretation of captured data. Within that period, forest fires would spread over larger areas. In order to overcome the disadvantages of MODIS-based forest fire detection system, a wireless sensor network-based system was formed. This system comprises of two main modules. One is placed in the monitoring area and the other is placed in the forest area. The forest area module consists of a temperature in the forest area. It sends a signal to the embedded web server. This web server continuously captures the signal and stores the signal for processing. Finally, the signal can be interpreted. Even the newly formed basic WSN based forest fire detection system had its own demerits. The first disadvantage is that it consists of an embedded web server that makes the system bulky and costly. The second demerit is that it uses radio frequency module, which is a basic radio frequency module, and it has several disadvantages. The first disadvantage of using a basic radio frequency module is high power loss. That is, when distance increases between two nodes, the power loss also increases. The second demerit of using a basic radio frequency module is that the current utilization is always high even in idle state. The third demerit of the system is that the low output produced by the photovoltaic cell is not utilized properly. The fourth disadvantage is impedance matching will not be maintained because the low power is not utilized properly. The final disadvantage shows that the system will be efficient only during bright light conditions and the system efficiency will be minimum in dim light conditions. In order to overcome the disadvantages of the existing systems, we proposed this new system. This system comprises of two main modules. One module is placed in the monitoring area and the other module is placed in the forest area. The forest area module comprises of Atmega 164A microcontroller, which is the heart of the system. Three different sensors, namely temperature sensor, pressure sensor and rain sensor, are used in this project. Temperature sensor is used for detection of the forest fire and it is directly attached to the microcontroller. The pressure sensor is used to detect abnormal prowling and it is attached to the microcontroller through instrumentation amplifier in order to boost the output voltage of the pressure sensor. And finally, the rain sensor is connected to the microcontroller with the help of IC7404, which is a simple NOT gate. And these blocks are used for implementation of optimized solar energy harvesting system. It comprises of a solar panel, the output of which is taken by the DC to DC input stage, and finally the energy is stored in the battery. The MOSFET driver is used to boost the voltage level in order to form the optimized output. The voltage measurement and pulse width modulation are taken care of by the microcontroller. Here, in order to transfer the signals from forest area to monitoring area and in order to do the switching actions from the monitoring area to the forest area, we use a Zigbee module, which is Zigbee series 2 from Digi International. Now we'll come to the comparison. This is the comparison between the existing system 2 and the proposed system. The first comparison is about the wireless sensor node. In existing system, they used basic radio frequency modules which had disadvantages like high current utilization and high power loss when distance between two nodes increases. In proposed system, we use Zigbee module which has minimum current utilization and it has low power loss when distance between two nodes increases. The second main comparison is related to the low amplitude DC voltage from the solar cell. During dim light conditions, this low amplitude DC voltage is not properly utilized by the existing system, whereas due to the implementation of optimized solar energy harvesting system, this low amplitude DC voltage is properly utilized by the proposed system, and because of that, impedance matching is maintained. That we make the solar energy harvesting system optimized with the help of an algorithm called maximum power point tracking algorithm. The fourth main comparison is about the solar harvester efficiency. Because of the optimized system, the efficiency is achieved to about 85%. The final comparison is related to the web server. Existing system uses embedded web server which makes the system bulky and costly. We overcome the disadvantage by implementing the server in PC itself with the help of LabVIEW. Now we'll come to the proposed system. We have divided the proposed system into 5 different modules. Now we will see the first module, which is the sensors module. The highlighted blocks are to be worked for implementing the sensors module. In this module we are going to see the sensors used with their working, then we will see the design of instrumentation amplifier followed by their interfacing. For programming we used embedded C programming, further we used AVR Studio 4, and for simulation Proteus is used. Finally, the hardware outputs are shown in the form of graphs. First we will see about the temperature sensor. Temperature sensor is mainly used for detection of forest fire, and the sensor used is a thermistor from ATC Semitech Limited. This particular sensor is chosen because of these features which are suitable enough to create the necessary requirements. So first programming is done with the help of Avia Studio 4, and with that programming the simulation is successfully conducted with the help of Proteus. Now we'll see the simulation. This is the simulation for interfacing the temperature sensor with the microcontroller. This is the simulation that is done, and here we have used a sine wave generator instead of the actual temperature sensor, and we'll write the program into the microcontroller and we'll run the simulation. Now we'll see the temperature as 26 degrees Celsius according to the program which is written into the microcontroller. In order to see a change in the temperature, the sine wave generator value is increased. Now we see a change in the temperature. So with this we can conclude that the program implemented for the temperature sensor interfacing is successfully done. And this is the circuit which is going to be implemented for hardware. The working of the temperature sensor is like this. When the system is switched on, it continuously senses temperature, and if the temperature is high, the resistance of the thermistor becomes low, and vice versa, and according to the values got by the microcontroller, the corresponding output is given to the system. Now this is the hardware output that was taken only with the thermistor. That is, directly different voltages are given to the directly different temperatures are given to the thermistor, and their corresponding voltages were taken. Now as the voltage increases, we from this graph we can see that the temperature increases. Now the temperature sensor is over. Next we will see about the pressure sensor. The pressure sensor is used for the detection of abnormal fouling. We use MPX2010D from Freescale semiconductor for detecting the pressure. Due to these features, we chose this particular pressure sensor, and this is suitable enough to do our abnormal fouling detection. Similar to the temperature sensor, the program is created for pressure sensing, and this is the interface done for the pressure sensor. The pressure sensor is connected to the microcontroller, and the LCD is also connected to the microcontroller in order to see the output. A particular value of pressure is set after the program is written in the microcontroller. When the simulation is switched on, we will see the corresponding value of pressure coming up in the LCD. So with this we can conclude that the pressure sensor program has also come successful. This is the circuit diagram with which the hardware circuit is going to be created. It consists of three parts. The first one is a pressure sensor. The next is the instrumentation amplifier, followed by the inverting amplifier. Two sets of amplifiers are used in order to amplify the signals so that other devices can understand the signals that are created by the pressure sensor. And this is simply the working of the pressure sensor. It works on inverse piezoelectric effect principle. Next we will see the instrumentation amplifier. This slide shows about the design and working of the instrumentation amplifier. This is the instrumentation amplifier designed according to these design equations. Now we will see the simulation of this instrumentation amplifier. The simulation was done in multisim. This is the input graph and this is the output graph. From these graphs we can see that the output has been amplified. The input has been amplified and the output voltage is higher than the input voltage. And this is the pressure sensor hardware output. That is, we saw the circuit of the pressure sensor. This is the circuit this is the pressure sensor circuit. For this circuit we got some outputs by giving different values of pressure, and that is a hardware output. And now from this output we can understand that when the pressure increases, the output of the pressure sensor also increases. Now we will come to the final sensor, which is the rain sensor. We will see about the rain sensor and inverter. Rain sensor is used to warn about landslides and floods that might occur during rainfall in forests. At first, the rain sensor is designed with the help of Express PCB, which is a PCB designing software, and with this PCB design, we have etched and implemented the actual hardware rain sensor. This is the hardware rain sensor which we have used in our project. This is the rain sensing circuit diagram which will be used in the hardware, and it works like this. When the system is switched on and if no rain falls on the rain sensor, the inverter output, that is the NOT gate output, will be low, so that the rain is not detected. Similarly, when rain falls on the rain sensor, the NOT gate output will be high, and accordingly the microcontroller will tell the user whether rain is detected or not. And now we have completed the module 1, which is a sensors module. We have explained the different sensors, and we have shown you the simulation and the hardware circuits which we are going to use. Next we will see about the optimized solar energy harvester. The highlighted blocks shows the optimized solar energy harvester system, and we are going to explain this block one by one. For maximum power point tracking module, that is our optimized solar energy harvester module, first we will see about the various MPPT algorithms available. From those algorithms, we have chosen the best algorithm as a perturb and observe algorithm. We will show the working of PNO algorithm. Then we will implement the PNO algorithm with the help of Simulink and MATLAB. And finally, the results of hardware implementation are also shown. Now we will see the MPPT algorithm types. These are the various MPPT algorithms available. Such the various algorithms are constant voltage method, constant current pulse method, open voltage method, PNO algorithm, incremental conductance algorithm, and temperature method. From all these methods available, perturb and observe method and incremental conductance method have excellent relative efficiency compared to other methods. So we are selecting these two among all these algorithms. Next, among these two, we have to choose one in order to implement to our system. If we see incremental conductance algorithm, it is a complex to implement and requires more time for processing. But PNO algorithm is simple to implement and requires less time for processing. Also, it is commonly used for many systems. So we infer that PNO algorithm is the best algorithm for our optimized solar energy harvesting system. Now we will see the working of PNO algorithm. When the system is switched on and if sunlight falls on the solar panel, first the operating voltage increases. Then a comparison will be done between the current power which is generated and the previously generated power. If the current generated power is greater than the previously generated power, the operating voltage will increase, else it will decrease, and this happens continuously. Having completed about the selection of the MPPT algorithm, next we will see implementation with the help of MATLAB. This is the MATLAB model that was implemented for the maximum power point tracking algorithm. Now we will see the different blocks available. The first is the constant insolation block. Here the value of 1000 shows that there is maximum sunlight or maximum light coming from the sun. This is the time varying insolation. This shows that various intensities of lights are coming from the sun. This is a switch which is used to select between these two types of insulation, and this is used in order to show the variation in the output. This is a photovoltaic module. This is the hardware module which we are going to use for testing, and this is the back of the hardware module. This contains the details of this solar panel, and these details such as the open circuit voltage are implemented in this photovoltaic module by double clicking it. Next, this is the multiplier. It will multiply the voltage and current to produce the photovoltaic power, and this is a maximum power point tracker. Two programs, one to initialize the reference current and one to update the insulation are associated with this block, and these are simply the outputs which shows the photovoltaic voltage, current and power. and this V out block is a desired output. We need a 12 volt to recharge the battery, so we have given us 12, and this is the main boost DC to DC control. It boosts the photovoltaic power generated to this 12 volt, and finally all the outputs are viewed with the help of this scope. Now we'll see a small video. Initially the switch is in the constant insolation position. Now we'll run the simulation, and here the efficiency is constant. Now we'll change the switch to varying insolation and we'll run the simulation. Now we see that the efficiency is varying, but it is maintained constant. These are the main outputs. So here the efficiency we are getting to about 85%, and in this graph the output power is maintained at a constant value. So this algorithm is a successful one. Now we have shown you the simulation result. Next we will see the hardware requirements. These are the hardware blocks associated with the optimized solar energy harvesting system. For MOSFET driver and DC to DC input stage, we use a Darlington pair, a MOSFET for switching. Then we use an inductor for charging and discharging. Then we use a rectifier for the conversion of AC voltage to DC voltage. Finally, potentiometers for controlling input and output voltages are also used. The pulse width modulation and voltage measurement are done by the microcontroller, and the maximum power point tracking is also taken care of by the microcontroller as we implement the MPPT embedded C program in this microcontroller. For energy storage, we use a conventional 12 volt rechargeable battery, and this is the solar panel that is used in this project. Next we will see the implemented hardware. This is the hardware for optimized solar energy harvester system. The solar panel is not shown here. The solar panel is attached to this board. We will see the components one by one. This is the microcontroller, which is Atmega 164A microcontroller. In this, the perturb and observe algorithm is written through embedded C coding. And this is the switching circuitry board. And this is the potentiometer with a resistor for V out control. Here V out we have to set as 12 volt, and these two transistors and these 5 resistors form the Darlington circuit for switching, and this MOSFET helps in switching. And this is a diode used for rectification of the AC to DC. There is another diode attached at the back side of the board, so the two diodes form a full wave rectifier, and we get higher efficiency. Now this is a capacitor attached to the circuit to remove ripples from the rectifier output, so that the output will be a pure DC. And this is a potentiometer for controlling the solar panel input. And this is the inductor. It is used to store and discharge the charge in order to make the output equivalent to V out. And this is a 12 volt rechargeable battery, and this is a voltage regulator IC7805 to give a constant output voltage, and this is IC7667. It is a dual power MOSFET driver. Some of the ICs in this board requires different voltages, such as minus 12 volt, plus 12 volt, plus 5 volt. So with this help of IC7667, we will be able to generate the different voltages which are required. Now this is the final hardware output of the optimized solar energy harvesting system. Now we will see this, and in this initially there is no insulation. If we give insulation, the input voltage is about 17 volt, and the output is maintained at 12 volt. Now we are keeping some object in between the insulation and the solar panel, so that the input has reduced to 3 volt, but still the output is maintained as 12 volt. This shows that this system has become successful. Now we have completed the optimized solar energy harvesting system, and here we have selected the MPPT algorithm from different types of MPPT algorithms, and we have developed that MPPT algorithm with the MATLAB and simulated the outputs, and finally we have implemented the hardware and shown you the final hardware output. The third module is a serial communication module. This module comprises of the two Zigbee modules, one in the monitoring area and the other in the forest area, and the microcontroller. Now we will see the flow
of the third module. First we'll see the serial communication between the microcontroller and the Zigbee with the help of an algorithm, which is the hardware algorithm. Then we'll see the implementation possibility of this hardware algorithm, and based on that we will reform the algorithm to show the serial communication in simulated form. We are doing the simulation of the serial communication in order to understand the processes that takes place during a serial communication, and this we are implementing with the help of 4 different softwares: Avia Studio 4, HapSim, Com0Com and Putty. Next we'll see about the selection of the best network topology, because a number of modules have to be kept or placed in the forest so that the entire area of the forest is covered, and those modules should be formed with the help of a network, and the best network topology should be determined in order to get higher efficiencies. Now we will see the algorithm for serial communication through Zigbee using the microcontroller ATmega164P. This is the actual hardware algorithm. It starts like this. First the system is switched on, and the sensors will get the inputs, and the input from the sensors are sent to the analog to digital converter of the microcontroller. Next the ADC will give digitized outputs. These digitized outputs are given to the USART of the microcontroller, and that will be passed to the Zigbee module. This Zigbee module is present in the forest area, and it communicates with the Zigbee module in the monitoring area, and finally we will get the signals in the PC based web server. But here the PC based web server must be implemented with the help of LabVIEW. Now it is not possible because still we have not implemented it. So we are going to reform this algorithm to simulate the algorithm with the help of various softwares. The modified algorithm starts like this. First there will be two consoles. One console will be for virtual serial port 1, that is the console in the monitoring area, and the next console will be for virtual serial port 2. Say this as the console of the forest area. So when we give input through one console, say USART 0 console, that input will be converted into equivalent binary code. After conversion it will be written to USART data register 0. This UDR 0 is present in the microcontroller. Now this data in UDR 0 will be fetched and will be displayed in the USART 1 console. Before displaying, the stored value will be converted back to ASCII format, after which this will be displayed. Similarly, if we give input through USART 1 console, it will be displayed in USART 0 console. If we give input to USART 0, it will be displayed in console 1, and it will console USART 1, and if we give input in USART 1 console, we will get output in USART 0 console, and that's the process. So again this process will be continued. It will be waiting for inputs, and based on the inputs from the console window, the condition will flow. Now this is a program for serial communication that will be written to the microcontroller. Next we will see about the various softwares that are necessary to simulate the serial communication processes. First is HapSim. HapSim stands for Helmi Savior Periphery Simulator. This HapSim acts as one of the consoles. Now we will see the steps for connecting HapSim to the simulated USART console. It starts like this. First we will execute Avia Studio 4, where we will write the embedded C coding. Next we will select the appropriate microcontroller. Then we will execute HapSim and change the configuration of HapSim to utrans.xml. This utrans.xml specifies the serial communication process. Then we will run the program in Avia Studio 4, and after which we will see HapSim acting as a transceiver. Now there are two windows. Suppose consider this as the first console and this as second console. If we type in the first console, the output will come in the second console. Similarly, if we select the second console and type in the second console, we will get output in the first console. This is the actual serial communication process. The data will be transferred between two different windows. But this is not the case that we need, because the serial communication has to take place between two different places, that is forest and the forest area module and the monitoring area module. So we have to use another terminal, that is terminal 2. Terminal 1 will be HAPSIM, and we have to form another terminal 2, and we have to connect both the terminals. Suppose terminal 1 is the forest area module and terminal 2 is the monitoring area module. Both these terminals are connected with the help of COM0COM. Only if we build this, the actual serial communication will be simulated correctly. Now COM0COM is a null modem emulator. It acts as an interface between the two terminals. Now this is the setup window for COM0COM. This CNCA2 and CNCB2 represent the terminals. Next we will see PuTTY. For terminal 2 we use PuTTY, such that it is connected to COM0COM. Now we will see how we are going to connect HAPSIM and PuTTY through COM0COM. It starts like this. We have to execute HAPSIM and load the utrans.xml file to enable serial communication process through HAPSIM, and we have to redirect the HAPSIM terminal to decide a port with the required baud rate. This baud rate, that is 9600, is the baud rate that is specified in the actual hardware, that is the Zigbee module, which has also a baud rate of 9600 bits per second. And similarly we have to open the PuTTY window and set the parameters like the port serial line number and the baud rate 9600. Next we will run the program in Avia Studio 4 so that the console 1 CNCB0 first console will come, and similarly if we give appropriate ports similar to console 1, we will get the console 2. Now the actual serial communication process takes place. Suppose this is the monitoring area and this is the forest area. If we select the monitoring area and type here, the output will be got in the forest area, and similarly if we type here, the output will come in the monitoring area. So this shows that the serial communication has taken place, and we have simulated the serial communication successfully. Now we will see about the selection of best network topology. Best network topology is selected for getting higher efficiencies during transmission between various Zigbee modules placed in the forest. Among the various network topologies available, tree network topology and mesh network topology have highest efficiencies compared to other topologies. So we are choosing tree and mesh. We are simulating both tree and mesh network topology for various outputs with respect to different parameters, and we are inferring which one is the best network topology. We are using OpNet modeler in order to simulate the results for various network topologies. Now we will see how to develop tree network topology. It starts like this. First we have to execute the OpNet modeler software and create a new project. Then we have to create a tree network topology scenario. For each and every Zigbee module in the tree network topology scenario, we have to set the parameters, which is similar to XB series 2 hardware module. And next we have to choose the data encryption standard, that is DES statistics, to simulate for various parameters. Next we have to set the simulation duration. Here the simulation duration is set for 1 hour, just to see the comparison. Finally we will execute the simulation, and then we will know the results. We will see finally in the comparison section. Similarly, for mesh network topology, the OpNet modeler software has to be opened. We have to create the mesh network topology, then set parameters similar to the Zigbee hardware module, choose the necessary data encryption statistics to get the desired simulations, then set the simulation duration and execute simulation to get the results. Now we will see the comparison. First comparison between tree and mesh network topology with respect to load in bits per second versus simulation duration. Here the blue color line shows the mesh network topology output and red line shows the tree network topology output. Now in this graph, mesh network topology has less load, which says that less congestion takes place. And similarly, in end-to-end delay versus simulation duration, the end-to-end delay between packets in mesh network topology is 0.001 seconds less than that of tree network topology. And similarly, if we look at the number of hops in mesh network topology, it takes only 3 hops to reach the destination, whereas in tree network topology it takes 4 hops for a packet to reach its destination. And from all these 3 comparisons, we infer that mesh network topology is the best network topology. Now the module 3 has come to an end. We have simulated the serial communication, then we have chosen the best network topology as the mesh network topology. Next we will see about the PC based web server. The fourth module is a PC based web server module, and PC based web server is implemented with the help of LabVIEW. We will see the steps involved in the development of this module. First we have to set up the serial communication hardware so that the actual process of serial communication can be seen in hardware through the PC based web server. Next we will see the required signals for transmission. Then with respect to the signals required, we will set up the LabVIEW server front panel, after which we will create the block diagram for the working of the front panel. Finally we will see the transmission process and its results. Now to set up the hardware for serial communication, we have to see the requirements. In the forest area, we require the Zigbee module and its associated power circuitry. The Zigbee module is connected to the microcontroller, and the microcontroller is connected with the sensors. Similarly, in the monitoring area, we require Zigbee and its associated power circuitry, and the PC where the server is implemented. But Zigbee and PC cannot be directly connected, so we are using a max 232 logic level converter. If this setup is done correctly, the wireless communication takes place successfully. Now we will see the hardware for the forest area module. This is the hardware circuit for Zigbee, that is a power circuitry. This is a voltage regulator connected to the Zigbee, and this is the simulation. The input is 12 volt and the output is got as 5 volt, because Zigbee operates at 5 volt only. And this simulation is done with Proteus. Next, this is the hardware for the serial communication setup. Here IC 7805 is the power MOSFET IC, and these capacitors are used for safety. Similarly, this Zigbee module is a module associated with the forest area, and the red color and the black color wire correspond to the power supply plus 5 volt and ground respectively. Now for serial communication, the yellow wire connects the PB2 of port B of the microcontroller to the receiver pin of Zigbee, and similarly green wire connects PB3 of the microcontroller to transmission pin of Zigbee. Now this is the hardware output. From battery we get 12 volt, and from the regulator output we get as 5 volt. Now forest area module hardware is over. Next we will see the monitoring area module hardware. This is the circuit for the monitoring area module hardware. First there is a pulse generator. This is used instead of a sensor or something like that, in order to generate the signal, in order to test the output. Then we will use the max 232 IC, and finally we will see the output in CRO, and this is the power supply circuitry. And now we will see the simulation. This is a small video. When we start the simulation, the yellow color and blue color signal shows the output. The blue color signal is inverted. The yellow color is the input to the max 232 IC, and the blue color is the output from the max 232 module, so that 5 volt is level converted to 8 volt, and it will be, or it can be interpreted by the PC. This is the hardware. This is the step down transformer for powering up the ICs, and this is the power supply circuitry. It comprises of a full wave rectifier and voltage regulator, and this is the max 232 circuitry with its biasing capacitors. Now we will see the final hardware results associated with the serial communication hardware of the monitoring area module. In order to understand the output, we have to look through this table. If the RS232 voltage is in the range between plus 3 and plus 5 volt, the output voltage of the Zigbee should be 0, and similarly if the output voltage of the Zigbee is high, the RS232 equivalent voltage should be in the range between minus 3 volt and minus 15 volt. So the output from Zigbee here is 3.96 volt, and the output from the corresponding pin is minus 7.48 volt, which is in the range specified as before. And similarly the output from PC is minus 8 volt, and after conversion it is converted to a 3.83 volt, so that the Zigbee can easily transmit or correctly transmit to the Zigbee of the forest area module. Now the final results of Zigbee and RS232 conversion are tabulated. Now the hardware has been set up. Next we will see the required signals for transmission. So from monitoring area to forest area we required 3 signals, that is asterisk, at and hash for thermistor or temperature sensor reading, pressure sensor reading and rain sensor reading respectively. That is, in order to fetch the temperature sensor reading we need a special character asterisk. If we send asterisk, it will go to the forest area module, fetch the readings associated with the temperature sensor and returns back. So if we scan asterisk, we can know the values associated with asterisk as the temperature sensor values, and similarly the other sensor values are also interpreted. And similarly from forest area to monitoring area there are 3 signals that are captured. Those are the sensed temperature, sensed pressure and the sensed rain signals. Now the required signals for transmission are completed. With respect to these signals, the LabVIEW server front panel is built. The front panel consists of various sections. First, this panel has switching controls. The temperature sensor is always on because that is the main application of the project, and the rain sensor and pressure sensor has on and off switches. We can switch off the rain sensor and pressure sensor if we, in case we have to save power, and for that we are using relays. This is the sensor status pane. In case if the threshold value is crossed, the sensor status pane in case if the sensors are switched on, the sensor status pane shows the corresponding status. Next is the monitoring panel. This shows the continuously updated value of temperature. Next is the environmental status panel. If in case the threshold values of sensors are crossed, this environmental status pane shows the corresponding alert. And finally the warning is displayed in this empty pane. The values are connected to the PC through the appropriate COM port, and the COM port selection is done in this pane. Next we will see the LabVIEW block diagram. The block diagram consists of two sets. First is the block for data transfer. This is the data transfer block. The gray lines show the infinite while loop. This is a millisecond timer value. Here we have represented the value as 100, which says that for every 100 milliseconds the values will be fetched and updated, and this is the input output port for connection to the COM port, that is hardware. Now this is a VISA. VISA stands for virtual instrument software architecture. Suppose in case if it is a temperature sensor, the VISA block sends asterisk to the COM port and returns values associated with asterisk from the COM port to the other blocks, and asterisk is a default value for temperature sensor. Next is a VISA read block. Here it reads 4 bytes of data from the COM port. The first byte corresponds to the special character, that is asterisk, and the next 3 bytes correspond to the value fetched by the temperature sensor. And this VISA block closes a device session, and the session starts again after 100 milliseconds. The read buffer stores the value that is fetched, and this is the string subset block. It reads the returned special character. There will be 4 bytes. The first byte, that is the 0th byte, will correspond to the special character, and the next 3 byte will correspond to the value returned or value associated with that special character. Suppose in 4 bytes, if first byte is star, then the system understands that the values returned are associated with the temperature sensor, and the next 3 values are the temperature values. Now this is a string subset block, and it reads the values of the sensor. That is this block reads the first value, and this 1 2 3, and the second string subset block reads the actual value. That is a type of the sensed value and the value of the sensor. Next is a decimal string to number conversion in order to display it to the user, and this is the indicator which is associated to the front panel. Now this is the comparison threshold temperature value. Here we have set the comparison value as 35 for example, but this comparison value or a threshold will change according to the different forest areas. For example, we have kept it as 35. Suppose if the incoming value is greater than 35, then warning will be displayed according to this alert condition. Now for temperature sensor we use asterisk, and for pressure rain sensor we use at, and for pressure sensor we use hash. These are the data transfer blocks for rain sensor and pressure sensor respectively, and this block will work depending on the value returned by this water sensor and pressure sensor conditions, which is associated with the switching blocks. Now we will see about the switching block. This is the switching block. It consists of 4 sub blocks. Why there are 4 sub block? If someone asks, 2 sub blocks are for on and off of the water sensor, and the next 2 sub blocks are for the off and on of the pressure sensor. Now this sub block is for the water sensor on. That is, if we click on, asterisk A will be sent to the main block such that the rain sensor will be switched on through the relay present in the forest area module. So after asterisk A is sent, that relay will be switched on, and after that at will be sent, so that the rain sensor values will be fetched and returned back. And similarly, if we click this off button associated with the rain sensor, asterisk B will be sent, so that the rain sensor relay will get asterisk B, and so at will not be transmitted because water sensor will be in off state. Similarly, asterisk O will be transmitted if pressure sensor off button is clicked, and hash will not be transmitted. And finally, if we click the on button of the pressure sensor, asterisk F will be transmitted, so that the pressure sensor relay will get switched on, after which hash will be continuously transmitted, which will fetch and return the values of the pressure sensor. Now the block diagram explanation is over. Now we will see the final transmission process and results. Now we will see the temperature sensing process. This shows the hardware part, and this shows the server part. We set the threshold as 28, so we are touching the thermistor so that the temperature get increased. When it crosses 28, it becomes 29. That is, it crosses threshold, and finally warning will be shown. So when it comes back below the threshold, that warning will go away. This is the final output, the warning shown because of increased temperature. And the next transmission process is related to pressure sensing. This is the forest area module, and this is the server. Now we are applying the pressure through pressure bag, so that it crosses the threshold, and abnormal prowling condition is turned as detected, and we will get a warning here. Similarly, the final transmission process associated is with the rain sensor. Here in rain sensor, if we simply keep any conductor, the circuit gets short, and finally we will get a rain sensor warning here. So when the rain sensor is short, the raining occurrence will turn to yes, and will get a warning in the warning pane. And this is the actual project. Now we have completed the PC based web server. So here we have shown you the serial communication hardware, signals involved in transmission, and finally we have implemented the LabVIEW server by explaining its front panel block diagram, and finally we have shown you the transmission results associated with all the three sensors.
Now comes the final module, which is the fifth module, and it is mechanical modeling. We have developed and implemented all the hardware components, but mechanical modeling must be done for successfully implementing the forest area module in forest without any damage. It has to be protected from the environment. So for the entire forest area module, mechanical modeling is done. Now if we take mechanical modeling, there are two types that should be developed. The first mechanical modeling should be done for forest along country borders, that is for modules which are to be placed for forest along country borders, in simple words, for accessible forest. And the next type of mechanical modeling required is for inaccessible forest. Now we will see the model for accessible forest. This is the mechanical model for accessible forest, and this is the ground level. In the ground we are erecting a pole made of steel. That steel pole has a hollow hole inside it, so that the wire connections can be made through that hole. Now in the position 1, the forest area module circuitry box is placed, and above that the solar panel is placed. Why solar panel is placed above the forest module circuitry box is that the circuitry box will be in a safe position from sunlight or rain if it is kept below the solar panel. And next, the rain sensor is placed besides the solar panel so that it is facing the sky in order to detect rain. Now in position 2, thermistor is placed. Position 2 is the optimum position for thermistor from the ground level and from the top, because if fire comes either from the ground level or the top level, in any way it will be detected if the thermistor is kept in the optimum position. Now in the final position, that is the third position, the pressure bag is kept, and the tube from the pressure bag goes to the forest module circuitry box through underground. Now this is the model for forest along the borders. But the most important thing is to make a mechanical model for inaccessible forest. This is very important, because in accessible forest we can easily implant the forest area model, but for inaccessible forest a different idea has to be made. Now we'll see the model for inaccessible forest. For inaccessible forest, we are taking a flexible monocrystalline type solar panel. The solar panel is flexible so that it can be turned into any shape. This solar panel is converted to a conical shape, and this box FAM stands for forest area module. The forest area module circuitry is contained in a box, strong box, and it is placed inside that conically shaped solar panel, and to the apex of that conically shaped solar panel a transparent parachute is attached. So this is the mechanical model for inaccessible forest, and in order to implement it in the forest, this entire module is carried by choppers, that is helicopters, and it is put into forest like this. The main reason why transparent parachute is chosen is because After landing of this module, the parachute may fall over the cone so that it will block the sunlight, but if it is transparent, the sunlight will pass through that parachute and hit the solar panel, so that the power will get generated, and the optimized solar energy system will utilize even the dim sunlight that comes through the trees. So this is a successful model for inaccessible forest. Now we have completed the entire project. We have seen the mechanical modeling for accessible forest, in which we have used a rigid solar panel, and for inaccessible forest we have used flexible solar panel. So hereby I conclude that we have completed the advanced proposed system for forest fire detection, and these are the achievements which are shown in the form of comparison between the existing and the proposed system, and everything in the proposed system is achieved, and they are explained before.